count for its mass. Once the neutron was discovered in 1932, a German physicist, Werner Karl Heisenberg, at once suggested that they, too, were present in the nucleus. Once it was understood that the nucleus was made up of protons and neutrons, it was easy to work out the mass and electric charge of the nucleus in terms of these particles. Obviously, the mass of an atomic nucleus depends on the number of protons and neutrons that it contains. Since the mass number of each proton and each neutron is 1, it is only necessary to add up their total number to get the mass number of that particular atomic nucleus. An atomic nucleus which contains 2 protons and 2 neutrons has the mass number 4. One which contains 8 protons and 8 neutrons has the mass number 16. One which contains 92 protons and 146 neutrons has the mass number 238. The electric charge of the atomic nucleus is just as simple to figure, or perhaps even simpler. The neutrons have no charge at all, so they can be ignored. Each proton in the nucleus, however, has a charge of +1. The total charge of the nucleus is therefore equal to the number of protons it contains. The nucleus with 2 protons and 2 neutrons has a total charge of +2. The one with 8 protons and 8 neutrons has a charge of +8. And the one with 92 protons and 146 neutrons has a charge of +92. The number of protons in the atomic nucleus is called the atomic number. Be particularly careful to notice that the atomic number and the mass number are 2 different things. The mass number describes the mass of an atomic nucleus and is equal to all the particles, both protons and neutrons, that the nucleus contains. The atomic number describes the electric charge of an atomic nucleus and is equal to the number of protons only that the nucleus contains. If you know both the atomic number and the mass number of a nucleus, you can figure out exactly the number of protons and neutrons it must contain. Suppose you were told that a certain nucleus has atomic number 20 and mass number 42. Well, then, since its atomic number is 20, the nucleus must contain 20 protons. To have mass number 42, the nucleus must contain 22 neutrons in addition to the 20 protons. And that is all there is to that. The frothy remainder, all the rest of the atom, outside the tiny central nucleus, is made up of electrons. These electrons within the atom are sometimes called planetary electrons. The reason for that name is that they were first pictured as little particles, whirling about the central nucleus much as the planets revolve about the sun. Actually, things aren't quite that simple. Modern theories of electron motion involve some complicated mathematics, which we don't have to worry about. For our purposes, the somewhat old-fashioned notion of electrons whirling about the nucleus like planets about a sun is close enough. The number of electrons in an ordinary atom is equal to the number of protons in the nucleus of that atom. It is equal to the atomic number, in other words. To go back to our usual examples, an atomic nucleus with 2 protons and 2 neutrons would be surrounded by 2 electrons. An atomic nucleus with 8 protons and 8 neutrons would be surrounded by 8 electrons, and one with 92 protons and 146 neutrons would be surrounded by 92 electrons. Now let us consider the charge of these electrons. The total charge of the electrons within an atom depends upon their number. Each electron has a charge of 1. 2 electrons would have a total charge of 2, 8 electrons a charge of 8, and 92 electrons a charge of 92. The number of electrons in an ordinary atom is equal to the number of protons in the nucleus, as we have seen. That means that the negative charge in the outer regions of the atom is exactly equal to the positive charge on its nucleus. Therefore the total charge of such an atom is exactly 0. That atom contains plenty of both positive and negative electricity, but there are equal quantities of each so that one neutralizes the effect of the other. The atom as a whole is uncharged. It is a neutral atom. What about the mass of the electrons? It is very little indeed. The most complicated atom we know contains 102 electrons. The total mass of all those electrons together is only a little over a 20th of the mass of a single proton or neutron. That is why people sometimes say that an atom is mostly empty space. Don't think for one moment, though, that this means the electrons are unimportant. Electrons are very far from really being empty space. In the first place, their charge neutralizes the charge on the nucleus. Secondly, although they cannot stop speeding subatomic particles, they can protect the nucleus from other atoms. When two atoms collide at ordinary speeds, they bounce away again after getting no nearer than each other's outermost electrons. In the process, though, the outermost electrons in an atom must take some punishment. As a result of heat, certain kinds of atomic collisions, or other causes, 1, 2, or even 3 of the outermost electrons can be chipped off an atom. Under very special circumstances, the inner electrons also can be removed. This happens, for instance, in the interior of stars such as our own Sun, where the temperature rises to millions of degrees. There, all the electrons are stripped off the atom. It wasn't until quite recently that mankind could duplicate that effect. In those stars where atoms are stripped of all their planetary electrons, the bare atomic nuclei can approach one another far more closely than the original atoms could. The planetary electrons are no longer there to act as protection or as bumpers. Such bare nuclei are called collapsed matter because matter composed of them can collapse together until the tiny nuclei are nearly touching. Collapsed matter takes up very little space. Suppose all the atoms in the whole Earth were stripped of their electrons, and the bare nuclei were allowed to collapse together till they were touching. The Earth would be squeezed into a ball a little over a mile in diameter. Yet the nuclei contain just about all the mass of the atom. That means that collapsed matter would have all the mass of the original matter even though it took up much less room. The little ball of matter, 1 mile across, into which we imagined all of the Earth to have been collapsed, would be just as massive as all of the Earth originally was. A piece of collapsed matter as big as a grain of sand would contain hundreds of tons of mass. The Sun and most ordinary stars, each of which is millions of times as massive as our small planet, contain only a small quantity of collapsed matter in their interiors. Some unusual stars, however, called white dwarfs, are made up of collapsed matter almost entirely. They are called dwarfs because they are unusually small for stars. Some of them are smaller than the Earth. Yet for all their small size they are as massive as other suns. You see, then, that the reason the matter about us is light and fluffy is entirely because of the electrons in the atom. They may be very light but they take up lots of room and keep the massive atomic nuclei well apart. Varieties of atoms are usually associated with one another in groups called molecules. Some molecules are quite small. The air, for instance, is made up mostly of molecules containing 2 atoms apiece. Larger molecules also exist. Some of the molecules in our body are made up of thousands of atoms. Molecules are always in motion. The molecules in the air about us, for instance, are moving at speeds close to 60 miles an hour. Even in solid matter, which seems to be hard and motionless, molecules are vibrating rapidly back and forth. The higher the temperature, the faster they move. Naturally, molecules moving like this collide with one another frequently. There may be millions and billions of collisions every minute. Colliding molecules often bounce apart without being in any way affected. Sometimes, however, changes result. A colliding molecule may have an atom or 2 knocked out of it, or it may exchange atoms with the molecule it strikes. It may stick to the molecule with which it collides, forming a new and larger molecule. Any of a number of other things may happen. Such events are often quite visible to us. We may not see the colliding molecules, but we can see the things that happen as a result. The molecules in an antacid tablet collide with one another and with the molecules in water. As a result there is a fizzing, and bubbles are formed. The molecules in a piece of iron collide with the molecules in the air, and as a result we see the iron turn rusty. The molecules in an acid collide with molecules in a piece of copper, and the copper turns green. When the temperature is raised, and molecules move more quickly, the collisions between them take place more frequently and with greater force. Visible changes take place faster. Paper bursts into flame. Wood chars and burns. Dynamite explodes. All these changes that result from colliding molecules are called chemical reactions. Chemists study these chemical reactions and try to figure out what different molecules will do in different types of collisions. From this they learn about the nature of the atoms that make up the molecules. It turns out that the way an atom behaves inside a molecule depends on how many electrons it has. If two atoms have the same number of electrons, they will behave in the same way. As we know, the number of electrons in the neutral atom is equal to the number of protons in the nucleus of that atom. It is therefore equal to the atomic number. For that reason, chemists divide up atoms according to their atomic number. All atoms with the same atomic number behave alike. Atoms with different atomic numbers behave differently. The simplest atom has atomic number 1. The most complicated atom we know today has atomic number 103. Atoms with all the numbers in between are known. This means that for the chemist there are exactly 103 different kinds of atoms. Chemists have given names to these 103 kinds of atoms, and they are referred to as the elements. Sample elements. Suppose we take the simplest atom. It has atomic number 1, that is, it has a single electron and no more. The name chemists give to such atoms is hydrogen. The name hydrogen comes from two Greek words meaning to give rise to water. The reason for this name is that, when hydrogen burns, water is actually formed. Most elements, and most other chemicals as well, usually have names derived from Greek or Latin. The names often describe something about the behavior of the chemical or where it was first discovered or some other fact about it. Hydrogen atoms pair off to form hydrogen molecules. If a large number of hydrogen molecules are collected in one place, the result is an air-like substance called gas. Hydrogen is the lightest gas known. It is only a 15th as heavy as air, so, when hydrogen is collected inside a balloon, the balloon floats in air just as wood floats in water. Balloons or dirigibles can be made large enough to carry tons of mass into the air. Hydrogen has one troublesome characteristic, though. It has a tendency to get itself involved in chemical reactions. In particular, the collision of hydrogen molecules with certain molecules in the air can result in considerable activity. If the temperature is high enough, hydrogen will react so quickly that it will explode. The hydrogen in the giant dirigible Hindenburg exploded back in 1937. That spectacular disaster was probably caused by the heat produced by a spark of static electricity. Because hydrogen enters into chemical reactions in this way, it is called an active element. The next simplest atom, of course, is the one with atomic number 2. It contains 2 electrons. This atom is called helium. The word helium comes from the Greek word for sun because, believe it or not, that element was discovered in the sun before it was discovered here on the earth. Helium is also a gas that is lighter than air. It is not as light as hydrogen, but it is still light enough to use in dirigibles. The useful thing about helium is that it gets involved in no chemical reactions at all. Helium atoms can collide with any molecule and just bounce off unchanged, even at high temperatures. They don't even group themselves with one another. They remain single atoms. Helium won't burn, it won't explode, it won't anything. It is an inert element. It is therefore quite safe to use in dirigibles. If you have ever seen the kind of small floating balloons sold at fairs and parades, you can be sure they have been filled with helium. You may be surprised that a single electron can make so much difference, but it does. Hydrogen, with one planetary. NOYL 9373_NOLOYDC Enolnan at Wolvi Unil at WOLV Unit Share Wolvi NJID 0Y Yen Gos Wolvi Jidwis SWOS. Electron in each atom will explode with the least encouragement. Helium, with 2 planetary electrons in each atom, won't react in any way no matter what. Consider the next element, the one with 3 planetary electrons. That is lithium, from a Greek word meaning stone because it was discovered in a mineral. It is not a gas, but is a solid under ordinary circumstances. Underscore 3 interesting elements are those with atomic numbers 6, 7, and 8. Element 6 is carbon. It is a solid, usually black material, which is very familiar to all of us since coal is a form of carbon. The word carbon, in fact, comes from the Latin word for coal. Carbon is more important to living creatures than any other element. Element 7 is nitrogen, and element 8 is oxygen. The atoms of nitrogen and oxygen pair off just as hydrogen atoms do. Nitrogen and oxygen are both gases. The air that is all around us is a mixture of the two, 4/5 nitrogen and 1/5 oxygen. The two gases differ in the way they behave. Nitrogen is rather inert, not as inert as helium, though, and oxygen is very active. When paper, wood, gasoline, hydrogen, and illuminating gas burn in air, it is the oxygen molecules with which they are reacting. If air consisted of pure oxygen and nothing else, these things would burn very brightly and rapidly indeed. If air consisted of pure nitrogen and nothing else, none of these things would burn at all. When you and I breathe, it is in order to draw the oxygen of the air into our lungs. The oxygen reacts with various molecules in our body and thus enables life to continue. The nitrogen is breathed in along with the oxygen, but it is merely breathed out again. We shall not go through the list of elements, talking about each one. There isn't room for that. Instead, we shall list the names of some of the elements. I think you will be surprised at how familiar these names are to you. Atomic number element 10 neon 50 tin 13 aluminum 53 iodine 16 sulfur 78 platinum 24 chromium 79 gold 26 iron 80 mercury 28 nickel 82 lead 29 copper 88 radium 33 arsenic 92 uranium 47 silver 94 plutonium. There are elements, of course, whose names are completely unfamiliar to anyone but professional chemists. Element 41 is niobium, 49 is indium, 54 is xenon, 59 is praseodymium, 66 is dysprosium, 91 is protactinium, and so on. Fortunately, we won't have to bother much with them. Families of elements. Although each element is different from all the others, there are family resemblances among some of them. For instance, sodium and potassium resemble each other closely. Both are soft, chemically active metals that are easily melted. Bromine is very much like chlorine. Both are active, poisonous chemicals. Argon is very much like neon. Both are inert gases. The reason for such resemblances rests on the arrangement of the electrons of the atom. These electrons are not scattered about the outer regions of the atom in any old way. They are distributed in layers. It is as though their similar elements chlorine are electron shells surrounding the nucleus of each atom, like the layers in an onion. Each electron shell is capable of holding a particular number of electrons. The innermost can hold only 2 electrons, the next can hold 8, the next 18, and so on. Let's consider the sodium atom now. It has an atomic number of 11, so that it has 11 electrons. These are distributed as follows: 2 in the innermost shell, 8 in the next, and 1 in the next. We can write that 2/8/1 and see that the total is 11. If we turn to the potassium atom, with an atomic number of 19, we find that its electrons are divided up 2/8/8/1 for a total of 19. Knowledge concerning these electron arrangements came through the difficult theoretical labors of men like the Danish physicist Niels Bohr and the Austrian physicist Wolfgang Pauli. For their work on the makeup of the electrons within the atom, both earned a Nobel Prize, Bohr in 1922 and Pauli in 1945. If we compare the electron arrangements of sodium and potassium, 2/8/1 and 2/8/8/1, we see that they are alike in that both have a single electron in the outermost shell. When two atoms collide hard enough to undergo a chemical reaction, it is the outermost shell that gets the hard knock. If two atoms have similar outermost shells, they will undergo similar kinds of reactions. The reactions won't be exactly alike because there are differences underneath, but they will be similar. Sodium and potassium are similar because both contain a single electron in the outermost shell, and they can be considered members of a family of elements that includes 6 altogether. One of these 6 is lithium, whose 3 electrons are arranged 2/1. Chlorine and bromine are similar because of their electron arrangement, 2. Chlorine, with an atomic number of 17, has its electrons arranged 2/8/7, total, 17. Bromine, with an atomic number of 35, has its electrons arranged 2/8/18/7, total, 35. Both have 7 electrons in the outermost shell. Then, there is the case of neon, atomic number 10, and argon, atomic number 18. The 10 electrons of neon are arranged 2/8, while the 18 electrons of argon are arranged 2/8/8. Both have 8 electrons in the outermost shell. All 103 elements can be divided up into families, some of which contain as many as 15 members, on the basis of their electron arrangement. In fact, back in 1869, a Russian chemist, Dmitry I. Mendeleev, arranged the elements then known into a table of rows and columns. He knew nothing about electrons, and neither did anyone else in those days. He arranged the elements, however, in such a way as to make those with similar chemical properties fall into the same columns. This was called the periodic table. For over 50 years chemists made use of the periodic table and found it very helpful in making sense out of chemical reactions. Then when they learned about electron arrangements, they found that Mendeleev, without knowing it, had arranged the elements in accordance with how many electron shells each possessed and how many electrons were in the outermost shell. Charged atoms. A few pages back, I talked about molecules colliding with one another. Sometimes, during these collisions, an atom in a molecule may lose electrons as a result, or perhaps pick up a few extra electrons. You may wonder if this change in the electron situation may not alter the atom itself and make it different from what it was. It does indeed. Suppose we take sodium, which contains, of course, 11 electrons. When a sodium atom collides with another type of atom, the sodium atom frequently loses one of its electrons. It is left with only 10 electrons. What difference does that make? For one thing, as soon as an electron is lost, the sodium atom is no longer neutral. Originally, its 11 electrons were exactly balanced by 11 protons in the sodium nucleus. The atom was uncharged. After one electron is knocked off, the 10 remaining electrons have a total charge of 10 while the 11 protons in the nucleus have a total charge of plus 11. The atom as a whole has a charge of plus 1. Take another case. Element 17 is chlorine, a greenish, poisonous, active gas. Its atoms pair off the way hydrogen, oxygen, and nitrogen atoms do. When a chlorine molecule collides with another type of atom or molecule, the chlorine atoms within the molecule frequently pick up an extra electron apiece and keep them. The chlorine atom ends up with 18 electrons, which have a total charge of 18. In the nucleus of a chlorine atom, however, there are only 17 protons. That's not changed, with a total charge of plus 17. The atom as a whole has a charge of 1. All atoms lose or gain 1 or more electrons if the conditions are right. Sometimes, as a result, molecules may have more or less than their usual number of electrons. Such atoms or molecules, or even, sometimes, atom groups that are parts of molecules, are not neutral. They have positive charges, if electrons are missing, or negative charges, if they have extra electrons. The size of the charge depends upon the number of missing or extra electrons. 51 Copyright atomic arrangements. These charged atoms or molecules can move with an electric current, under the proper conditions, just as electrons do. Those with a negative charge move in the same direction as electrons. Those with a positive charge move in the opposite direction. Because these charged atoms or molecules move in the presence of electric currents, they are called ions, from a Greek word meaning to go. According to the type of charge, there are negative ions and positive ions. When a positively charged particle, such as a proton, flashes through matter, it can attract electrons away from the atoms it passes. A negatively charged particle, such as a speeding electron, can repel electrons away from the atoms it passes. In either case, the atoms have fewer than the proper number of electrons and become positive ions. It is these ions that make it possible to track the speeding particles by means of water droplets in a cloud chamber or vapor bubbles in a bubble chamber. An uncharged particle, such as a neutron, neither attracts electrons nor repels them. It lets them remain in place and therefore does not form ions. That is why neutral particles cannot be detected as easily as charged particles can be. An electric current can be carried by ions present in water just as it can be carried by electrons present in a metal wire. The electricity in the storage batteries of automobiles is carried partly by ions. Very pure water is not a good conductor of electricity,